Hey everyone, so today we've got a seriously cool explainer lined up. We're going to completely demystify something that honestly feels a bit like magic. How we take the raw, untamed power of nature and transform it into the electricity that lights up our cities, runs our homes, and basically keeps our entire modern world spinning. We are talking about the incredible mechanics of hydropower.
Right off the bat, let's ground ourselves in reality here. Just look at the Hoover Dam in the US. Take a second to really appreciate the awe-inspiring scale of this thing. It's an absolute prime example of massive human engineering designed for one specific purpose, harnessing the sheer force of water. When you stand next to a structure like this, you quickly realize we aren't just building walls out there, we're building colossal energy-harvesting machines.
Now, what's wild is that the physics here, they literally don't care if the structure is natural or man-made. Whether we're looking at natural wonders like Niagara Falls, or huge river dams on the Nile, or even those mountainous dams on the Euphrates River in northern Syria, the core concept is exactly the same. We're exploiting falling water. If water's dropping from a high elevation to a lower one, there is energy just waiting to be captured.
So to wrap our heads around this giant machine, here is our roadmap for the explainer. We'll start with the power of dams, weigh the pros and cons of hydropower, track the actual journey of water, dive into the physics and a literal danger zone, and finally, look at something super cool, mountain batteries.
All right, kicking things off with part 1, the power of dams, and how we convert altitude into actual electricity. The process of getting electricity from water is just a brilliant chain reaction. Think of it like a relay race of physics. Step 1. You've got water sitting way up high in a reservoir that's packed with potential energy. Step 2. You let it drop. As it falls, that potential energy turns into kinetic energy, right? The energy of motion. Step 3. That rushing water smashes into a turbine, transforming into mechanical energy as the blades spin. And finally, step 4. That spinning turbine turns a generator, pushing out electrical energy. It's just so elegant.
Moving right along to part 2, pros and cons of hydropower. Because, there are definitely trade-offs when you're trying to harness an entire river.
It's a massive balancing act, really. On the pro side, you've got exceptionally clean energy, super low daily operating costs, and these things last practically forever. But their absolute superpower is response time. I mean, these plants can ramp up from producing 20 megawatts to 150 megawatts almost instantly if the grid suddenly needs it. But we got to look at the cons. The upfront construction costs are just astronomical. Plus, you are entirely at the mercy of external factors. If there's a bad drought, or say the Ministry of Irrigation needs to hold back water for farming, your multi-billion-dollar power plant is basically stuck running way below capacity.
Which brings us to part 3, the journey of water. We're going to literally follow a single drop right through the guts of this machine.
So the journey follows a really strict sequence. It starts up top in the massive reservoir, our giant battery of potential energy. When the gates open, our water drop plunges down this massive, slanted pipe called the penstock, picking up terrifying speed. Then, bam, it violently crashes into the turbine, spinning the blades. Finally, it shoots out through the draft tube. And that last part is absolutely crucial. The draft tube safely pulls the water away so it doesn't back up and, literally block the rotation of the exact turbine it just spun.
If you look at this cross-section, you can visually trace out those exact steps. You've got the water sitting way up high on the left, rushing down that diagonal penstock, but I want you to notice the vertical axis right in the center. That is the heart of the whole setup. You have the spinning water turbine down below, and it's directly connected by a single vertical shaft to the electrical generator sitting high and dry up top. It's incredibly robust.
All right, on to part 4. Let's talk about the physics and what engineers call the danger zone, specifically the threat of cavitation. Now, I promise not to get bogged down in textbook math here, but I want you to grasp the big picture. A plant's power output basically comes down to multiplying a few key variables together. You've got the water head, which is really just engineer speak for how far the water drops. You multiply that by the flow rate, which is the volume of water moving through. Throw in gravity, the density of the water, and finally the station's efficiency. Because actually, due to friction and heat, these stations usually run at about an 85% efficiency rate. To put those numbers into perspective, if you maximize those exact variables, massive height, massive water flow, you get the world's largest dam over in China, which generates a mind-boggling 18,000 megawatts. That is an almost incomprehensible amount of energy just from letting water fall. We're talking enough to single-handedly power millions and millions of homes.
But there's definitely a dark side to all this power. When you push these limits, you build up extreme tension within the system. So what happens when the water pressure and speed get way too high? What happens when a dam reaches what engineers ominously refer to as the critical head?
Well, hitting that critical height triggers something totally destructive called cavitation. And this is where physics gets really weird. According to Bernoulli's principle, when water moves at these super intense speeds, the localized pressure drops severely. It drops so low that the water literally boils at room temperature, turning into gas bubbles. But those bubbles don't stick around. In a fraction of a second, they violently implode right against the steel turbine blades. These microscopic implosions act like tiny bombs. Over time, they will completely eat away at solid metal, eventually forcing a catastrophic shutdown of the entire plant.
Okay, finally, Part 5, Mountain Batteries and the Absolute Genius of Pumped Storage Stations.
The solution engineers came up with to store this energy is just incredibly clever. You can basically think of these setups as giant mountain batteries. Here's how the loop works. Sometimes the power grid has extra electricity, like say it's super windy at night and nobody's using power. Instead of wasting it, the plant uses that surplus to run massive pumps. Step 2, they literally pump water from a low lake all the way back up the mountain into a high reservoir. They're basically charging the battery with potential energy. Then, step 3, hours or even months later, when the grid really needs power during peak hours, they release that stored water back down. Step 4, it spins the turbines and feeds the energy right back to the grid.
Looking at this turbine room, check out those massive yellow housings. It's wild to think these machines can just run this cycle over and over, daily, weekly, seasonally. They are essentially gigantic reversible batteries. And this isn't just some far-off theory either. This exact pumped storage technology is actively being studied for Mount Ataqa in Egypt right now, which could turn a huge geological feature into a vital energy reserve for millions.
And that actually brings us to the end of our explainer today. As our global need for clean, reliable power keeps growing, and as we try to move away from fossil fuels, it leaves us with a pretty fascinating thought to ponder. As engineering keeps evolving, how many more mountains are we going to turn into giant natural batteries to power our future cities? Definitely something to think about. Thanks so much for exploring the mechanics of hydropower with me today.